Okay, now that we are ready with the concept of partial derivatives, we need to take a look again to the limits and continuity. It's quite the same as you studied the limits and continuity for differential for single variable. The only difference that now we have, instead of having a line when you were working on the limits on the single variable, you had something like this, and you were asked to work between a limit on a line. Okay, that was more like a set of values between some volumes for x, and it was a kind of delta, and this was the delta that belongs to epsilon. Here is the same, but we are not working anymore in a line. Now we have a region, and that's the reason why I'm including this picture here to show you that now this is the x and y. So this is our um, independent, and this is the set of values of x and y. And in a third plane, we have this function, which is the rule that transforms the combination of these two variables into a z variable, which is now our dependent. Okay, so according to this region, we can have any value that is close to some point, in this case a comma b, and we will have an effect if this is continuous and the limit does exist. We will have a result on the z variable, just like in the single variable, a value from L, which is the limit, plus and minus an epsilon value, which is some kind of delta that belongs to some delta uh, lowercase that is inscribed in this region over here. The formal definition for the limit is right here, is let f be a function of two variables, in this case this function over here, and holds domain D. The domain D is all the values of x and y that are in the range of interest. So do variables where domain D includes points arbitrarily close to a comma b. So this is this encircled in this orange line. This is the domain of the x and y variables, and all this area over here is the coordinates or the values that are part of the domain of y and part of the domain of x, and the combination of these two is represented here by this area. So if the limit exists, we will have that the limit of x comma y as x comma y approaches a point given AB is equal to L, and the plus minus epsilon here will be proportional to this plus minus delta in the independent variable domain. So the limit when x comma y approaches a comma b is going to be, for the function that is a function of x and y, will be equal to L. So, and this is the formal definition of the limit in this multivariable. Okay, and If for every number epsilon greater than 0, which is this value here, this is epsilon greater than 0, it means that is some positive value to the right and to the left of L. So this is a kind of neighborhood. If for every number epsilon greater than 0, there's a corresponding value delta greater than 0, such that the absolute value of f x comma y minus L is less than this epsilon whenever the values for x and y belongs to the domain, and then we can say that the limits exist, and the range of values for this region will be greater than 0, because we cannot have any value less than 0 here, so we need to have something to calculate and have this L result, and less than delta. And the formula to calculate the limit is the same formula that you were using to calculate the distance. If you see, this is the distance of 2 points in a 3D space. Okay. If you have a 3 variable function, you will have 3x minus a squared plus y minus b squared plus z minus c squared, and so far so on. In this case, just to illustrate the nature of the limit, we have x minus a, which is this one, and y minus b, which is the distance of the radius from this point AB all to the values that are corresponding to this plus minus epsilon in the dependent variable. This image here, I think it's more clear. We have these coordinates from x and y, and we have the z variable. And as I told you before, the combination of these x and y variables is forming this surface. And this is the projection of the contour plot for all the values that we are working for to calculate the limit. And this region over here is those values plus and minus L that belongs to these values of plus or minus delta to define the limit. Okay, talking about continuity, if you know in single variable you were working with some functions that were something like this. And let's say here this is x and this is y. And when you were working with this, you might find that sometimes, for example, in this particular case, let's say that x equals 3, and for x equals 3 we have two values of y, maybe have this one, and there's a gap here. So this function is not continuous. And if this principle is not met, so sometimes the limit will not exist. Okay, because there is no continuity on the function in the domain of x according to y. In the multiple variable is the same scenario. For example, in this case, we have this function h of x and y, and equals the arctan of y divided by x, and this is the plot or the graph for that function. If you see, when x equals 0, we have some situation very similar to this case, but here in the 3D plane, we have this surface, and there is a discontinuity between these values of x, when the positive values, and the negative values of x. So in this case, it's not defined for 0 because we have this lip from this value up to this one, and this is not continuous. So it is easy to find when the function is or not continuous. Uh, Sometimes it's enough to have a plot of it, but otherwise you need to do some calculations to find out if there is or there is not continuity. Okay, so this is a brief explanation of what the limits and continuity are for these multivariable calculations. As you see, they are very similar to the first ones that you were studying at the beginning of your course. Please let me know if you have any questions or comments. I'll be waiting for them, and stay safe.